Anyway, I'll just go ahead and get started. I'm Dr. Chris Jorgenson, and you can see the flyer up on the screen. And so this is a talk about that involve both math and some things I noticed that were in math and music. And I have a bachelor's of music degree. And yeah, if you're coming in just now, you have it's like a handout to fill out during the lecture. You can get extra credit from, and anybody, whether you're in my class or not, can partake in the salted peanuts, lightly salted cashews, napkins. So if you're allergic to any of those three things, then stay away from you're allergic to peanuts or napkins. Make sure you're not exposed to that, so you know what's here. All right. Yeah, let's just go ahead and move on here. Let's see how this works. Okay, there we go. All right, so this is called Harmony, the Harmonic Series, and Torricelli's Trumpet. And Evangelista Torricelli lived in the 1600s, and he was an Italian physicist, a mathematician. He invented the barometer that he's holding there, and he was a student of Galilei. And the quadrivium is part of the 7 liberal arts, and the quadrivium is the name given to 4 classic areas of study, the ancient Greeks, consisting of geometry, number theory, astronomy, and music, and these all relate to mathematics. And then the other parts of the trivium are more related to English, grammar. Anyway, so what happens when one plucks a string? I want to have some guitar and a trumpet to show you. So it's not just things we're pointing at and looking at. What happens when one plucks a string? So we can pluck a string to kind of show, or so you can hear, but there's some other diagrams here. You can see a string vibrating there. And we'll use that first picture as what we'll call the fundamental, the main string. But a string vibrates, different parts of the string will vibrate, and you have like in 1 second it might vibrate many times. That's a diagram for that. And this represents a vibrating string where there's some decay. It gets quieter and quieter. And so the frequency F is the number of oscillations per second of a string L meters. That's the length L meters, stretched at a tension of T newtons, and with a mass M kilograms per meter of length, which satisfies this equation. And I started looking at that, and I realized eventually realized that you can kind of represent all of these things with like a guitar, because when you change the length of a string, if the length gets longer, if L gets bigger, then F gets smaller, and the frequency goes down, and then the tone gets lower. The lower the frequency is the number of oscillations per second, so the lower the frequency, the lower the pitch. And so the way this formula is written, because L is in the denominator of the fraction, when L gets bigger, F will get smaller and lower. So we can change the L here. But tension we can also change, because when you tune a string, if T increases, then F will also increase. So if you increase the tension, I'm increasing the tension of the string, then that increases the frequency. When the frequency increases, the pitch goes up. So there's more of a direct relationship between tension and frequency. And then the mass, if you think of all the guitar strings, they're all the same length, and they all have about the same amount of tension, but the mass is different, because the ones with the bigger mass give you higher the mass. If M gets bigger, there we have an inverse relationship again. If M gets bigger, then F gets smaller, and the frequency goes down, and the pitch gets lower. So if you go from the highest string to the lowest string, you can see the mass gets bigger, and then the frequency goes down, and you get a lower pitch. So you can kind of recognize all those things with the guitar, all these different variables with the guitar. All right. So, so if we have a fundamental, and we'll call that length L sub 0, then the frequency is F sub 0. Each string, anytime you pluck a string, different parts of the string are vibrating, different lengths of the string are vibrating. And so if you put in for L sub 0, 1/2 of L sub 0, then if you work this out, that's like half the string, look at half the length. So that would give you like, the tone would go up an octave. So the length gets smaller, then the tone gets higher, the frequency gets higher, call that F sub 1. And then if you work this out and flip and kind of take the reciprocal, you know, because you have 1/2 of that and kind of flip it around, you'll have 2 times F sub 0, 2 times what we had at the top line, 2 times F sub 0. So it doubles the frequency when you half the length. Cut the length L sub 0 in half, it doubles the frequency. But you can also tell the sound, the musical tone sounds the same, right? It's really the same pitch, but an octave different. And then also, when you're just plucking a string, you get like a perfect fifth. You get, or if you cut the length by 1/3, then you get a perfect fifth plus an octave. So 1/3, a perfect fifth is really 2/3. So here's, but if we instead of using 2/3 of the width and 2/3 of the length, we cut that in half and go to 1/3. That'll go up to here. There we are. Then we change the octave. So this is 1/3 of the string. That gives you 3 times the frequency of the fundamental. And so that's an octave and a perfect fifth above the fundamental. And so if you look at different whole, what I'll call unit fractions of the string, if you like 1/2, that gives you the first harmonic. That's 2 times the frequency changes by 2 times the fundamental frequency. You go up an octave, and just as a pitch example, we use C as the fundamental, but you go up an octave, right? So there's, and so if the next harmonic, so these numbers here are the same as the numbers in this table. So the third harmonic we kind of showed there was 1/3 fraction of the string, 3 times the fundamental. It's an octave plus a perfect fifth. You go up a G, and I'm using colors that often are associated with steps of an octave scale that are also colors of the rainbow, Roy Gabiv. And so Roy, red's the bottom, and Gabiv B is blue, and that's the 5th step up. And so so you go from C up to C to then up a perfect 5th to G, then up a perfect 4th to C again, to the 4th step. And then you go up a major 3rd. So that's the Roy yellow, R red, orange, yellow, the 3rd step. It's a major 3rd plus 2 octaves to C. And so that's the 5th step, the 4th harmonic. Then you go up a minor 3rd to the next harmonic, which is 1/6, perfect 5th plus 2 octaves, back to G. So those are an octave apart. 1/3 to 1/6. 1/6 is 1/2 of 1/3, right? And then the red ones are, you have 1 and 1/2, and 1/2 of 1/2 is 1/4. Now the next harmonic is a flat 7. It's like B flat. If the fundamental was C, then the 6th harmonic is a B flat. That's a minor 7th plus 2 octaves. And I'll try to play this with my trumpet, but okay, the trumpet, I don't want to go too much into different things, but if the trumpet's a B flat instrument, so if I play it, and these were tuned last night, I didn't check them today, but it should sound like this. So I play the first 8 steps that are there. And I'll play them with my guitar so you can hear what I was. If I play with the trumpet, you'll hear what I'm trying to play. Okay, it'll sound like this. There's that major 3rd. There's that flat 7, B flat. then the seventh harmonic. Play that again. That actually makes like a B flat 7 chord. I'm doing B flat because I'm going to play C with my trumpet, and the tones will be the same if I play B flat with on a regular C instrument here. Okay, let's see if I can play that with the trumpet. I picked up the trumpet the other day and I went all the way to high C, but I can't do it every time. So, all right. So what you can do with a string, you can also do with a column of air. You can have that same type of overtone, the overtone series. Now with the trumpet, who's seen a bugle before? You ever hear them play reveille like at Army camp or something? They have a trumpet that doesn't have any valves, and so they can only a bugle can only play these notes. And so a trumpet puts in valves to change the length enough to where you really get 7 bugles that differ by a half step, so you can cover all 12 notes. And yeah, that's about the same, B flat and C, because I think to keep the trumpet from being too big, it's a B flat instrument, so when it plays C, it sounds like a piano or a guitar like B flat. So anyway, it's a B flat instrument, like a clarinet or a tenor sax or B flat instrument. Wow, just got it, barely. All right, sorry. So those are the only notes you can play with an open, with no valves at all. You just play. That's the first 3 notes. No, I'm not playing 1. I'm not playing that one. I can't get that low, but I'm starting here at 2. What I just played, what you heard, I probably can't play it again, is 2, 3, 4, 5, 6, 7, 8 up to the high C. And that's all you can play with an open. So you need to put in, now look here, the trumpet, if you push the second valve, that'll increase the pipe, the length by this amount, and you can play, it'll go down half a step. Then you can do the same thing and build a overtone series on the B flat with the. And then if you go down, push 1, see the 1 valve adds a little bit more pipe, and then 3 adds even more pipe, and so you can change the length of the trumpet to cover all the notes. Now 1 and 2 add up to 3. So you might think if you're a mathematician, you might get, because each valve, there are 3 valves, and each valve has 2 positions, closed or open, right? Just kind of binary languages, 0 or 1, right? Open or closed. So you think you might have 2 times 2 times 2, 8 different positions, but 1 and 2 together add up to 3. So so 1 and 2 are the same as 3. And usually if you push 3, and I don't really know why, but you have to extend this third valve pipe right here with this ring just for tuning purposes, but can't get that lowest note now. Okay, so when you go from open, then you push 1 valve, that's the shortest valve, that'll decrease by half a step. Then if you push 1 by itself, that'll decrease by a half more step. Then if you push 1 and 2, that'll bring the short one out with the 1, and that'll give you a lower, 1/2 lower step. And then if you do 2 and 3, 3 is longer than 1, that'll bring it down half a step more. And then if you do 1 and 3, 1's longer than 2, so that'll bring it down half a step. And then when you finally push all 3 down, that'll open them all up, and you're at that lowest position there. So you get 7 different positions, and if you have an overtone series based on 7 notes that are a half a step apart, then you can get all 12 notes. And so the higher you get alternate fingerings for the same note if you play, the higher you play. So I feel like I can just play those notes again. Sorry. For some reason I have trouble playing the low notes this morning. Anyway, so now what else did I want to say about the trumpet? I need some valve oil, now it's starting to get stuck. Yeah, so there's really interesting things going on. Oh, yeah, so see if I can play the whole octave, and then I'll try to come down chromatically. You remember my fingering. Anyway, so there's really some neat things going on. So if you just play a trumpet without any changing of the finger, if you pick a fingering and play it, you'll just get the overtone series. You won't get but those overtones correspond to unit fractions of the string. Okay. Okay, so let's the next one. If you keep going, it goes up another octave, and the notes are closer and closer apart. So if you play higher, you can almost use any fingering for some of these notes. Because a whole step, another whole step, a half step, minor second, major second, minor second, minor second, minor second. And anyway, so it's kind of interesting there. Okay, so now what if you started, so here's my laboratory. It involved the guitar and a tape measure. So let's see what we have here. So I measured, the whole neck of the guitar here. And these pictures are from 10.5 years ago. If you're wondering why I'm wearing a leather jacket and the hat, I'll show you later. Without it, I just thought it wasn't stylish enough. Okay. So here I measured the frets. I went ahead and used inches, eighths and halves and quarter of an inch. And so if you take the whole length, it was 25 and 5/8 inches. That's the whole from the nut to the bridge. And you play the whole thing, the ratio is 1, you get low E. So now we're building on E because it's the lowest, kind of the nature of the guitar. All right, now if you go up half, we've talked about that already. That's like, the length is, 12 and 13/16 inch. And take that length over the whole length, and you get a half. Gives you an octave. Okay, so here's where we're getting the unit fractions in the harmonic series. There's 1 and 1/2. And then if we go up another half, so once we get too high, we don't have the fretboard. We run out of fretboard. We have to use our ears to measure. So how do we measure here? We all paid it? Okay. This might be interesting. I know. Pay a little attention here. That's why you're here, right? Okay, here's a fourth. Now what fret is that? Question mark. We don't know what the fret is. That's 1/4, another octave. So we got 1, 1/2. So we have to listen to know where I'm measuring. So that's 1/4. My ears tell me that's 1/4. That's another octave. Now what about 2/3? That's the perfect fifth. From E, you go up to B. So that length is 17 and 1/8 inch from here to here. From that, after I did all the measurements, I could just use those numbers. Now if you go up a whole octave, oh wait, no, we're still on the fretboard for this. So that'll give you 1/3. That's the next fret. So that's 8 and 5/8 of an inch over 25.65. That gives you 1/3. 1/3 of the string. 2/3 is another octave. Okay, what if we go, what's 1/2 of 1/3? It's math. What's 1/2 of 1/3? What number added to itself gives you 1/3? Oh, 1/6. All right, so we'll go up. So we'll get that unit fraction, 1/3 of. Now there's 1/6 of the string. The length, well, to the forefinger. I'm not going to measure it. I didn't have the frets for that. So that's perfect fifth plus 2 octaves. So there we have 1/6, we have 1/2, we have 1/3, 1/4, What are we missing now? Well, infinitely many, right? So now we could play up to the perfect fourth. That's 3/4. And we had different, in music school, back when I went to in the early 80s, we had different songs to help us remember the intervals. But we can't get unit fractions from 3/4. We get 3/8, 3/16. All right, so we'll go to the next one, and that's 4/5. That's a major third. 4/5, 20.25 inches over 25.65. That's about, it's approximately 4/5. Because some, music harmony is really a compromise between natural tuning, what you hear, and equal tuning, where we needed equal tuning and well-tempered tuning back in Bach's day in order to play in all 12 keys, because you couldn't do that with mean tone tuning in the old days. And then more later in the early 20th century, they started using equal tempered tuning, where they pretty much divide up the octave in equal lengths and creates a geometric sequence that goes from 1 to the 12th root of 2 to the 12th root of 2 squared to the 12th root of 2 cubed, and you get up to the 12th root of 2 to the 12th, which is 2, and now you're at the octave. But anyway, all right, so major third is 4/5. So what's half of 4/5? Go up an octave, 2/5 of the string. 2/5, right? And we get another unit fraction from the harmonic series if we go up another octave, but we'll run out of fretboard here. Have to listen for there we are. That's going to be 1/5 of the string. You can hear it though, right? You can use your ears to measure. Okay. Yeah, 1/5. That's major third plus 2 octaves from the bottom E string. There's major third in 1 octave, major third in 2 octaves. Hear that one? All right, so you're wondering, why did I wear a hat? Well, 10.5 years ago, I took these pictures and I thought, no, it's just not snazzy enough. All right, anyway, so I decided I needed some more, needed to be a little more stylish. So I put the leather jacket and the hat on while my wife took pictures of me. See? A little more stylish, huh? All right, anyway. Okay, so the harmonic series, again, but more mathematical this time. So the harmonic series is the sum of the infinite number of unit fractions, 1/2, 1/3, that come up in music. That's probably why they call it the harmonic series. Comes up in music. 1 and 1/2 and 1/3 and 1/4, 1/5, 1/6, and so on. 1/7, 1/8. Okay, and so we'll denote the first partial sum is just the first. We're going to add these up. Mathematicians saw these. Hey, harmony. Yeah, well, let's add them up. Because they're mathematicians. All right. So in the second partial sum is 1 and 1/2, and that's 3/2. Okay. The third partial sum, you add up the first 3, 1 and 1/2 and 1/3. That equals 11/6 or 1 and 5/6. And then you go from there. The 10th partial sum doesn't even get to 3. So this series, if you think of it in terms of partial sums, it can be like a sequence of partial sums. Then you'll get, these sums will increase, but very slowly. And then we have the nth partial sum. So to really do math, you need to work with a finite sum, because if you try to do math with an infinite series, which is just the word you use when you have an infinite sum, a series, then some of the math properties break down. But if you're adding or doing math with a finite sum, then no problem. It's just a regular sum. And so here's the harmonic series. Yeah, the harmonic series grows very slowly. If you, the 100th partial sum is just over 5, 5.187. And the first 1,000 terms, the 1,000th partial sum is just barely over 7, 7.486. And this actually, there's a way to do this using old-time mathematics. You don't have to use supercomputers or anything to actually figure out how many terms do you need to get like to 15. And this is in sort of a senior analysis class, the method that's being used, but it goes back just a few hundred years, actually, before they had computers. But just to let you know, you didn't have to use supercomputers to do this. I did this using, well, sometimes you have to use just a basic calculator, maybe, but scientific calculator. But 1,835,420 terms, or let's say that the 1,835,421st partial sum of the harmonic series just to get to 15. And to get over 100, the n has to be equal a 44-digit number. So these I actually got from a math. This one, and this last one I got from a math book. This one I got from my senior analysis class. It's something we did in senior analysis. All right. Because of this slow growth, people wondered to what number do the series converge to? They, it's so small, it must converge to something. And a lot of times series will narrow in on one number, and that's called convergence. But then one of the Bernoulli brothers, so this goes back a few hundred years, he was actually the teacher for Leonhard Euler, who lived in the 1700s, and he really taught people how to do math with complex numbers, and he was the first to use the Greek letter pi for the number pi, and he was the first. So Leonhard Euler is one of the best and most prolific, certainly the most prolific mathematician of all time, and he went blind in one eye, then he went totally blind, but he had children that helped him to get by anyway, but so his teacher was one of the Bernoulli brothers, Jacob Bernoulli. So this proof, I'll show you that it's that the harmonic series diverges comes from him. It's credited to him. So the second partial sum is 1 plus 1/2. So that means the 2 to the n partial sum is greater or equal to 1 plus n over 2 when n equals 1. We know that now. So we're going to try to prove this, or I'll show you why this is true. So the fourth partial sum, that's 1 plus 1/2 plus 1/3 plus 1/4. And that's greater than, if you write the same sum but change 1/3 to 1/4, then you have a smaller sum. But this is equal to 1 plus 1/2 plus 2/4, which is 1/2. And so this shows that the 2 squared partial sum is greater than 1 plus 2/2, because you have 1/2 here, 1/2 there. And you can show that really so therefore the 2 to the n partial sum is greater than 1 plus n/2 when n equals 2. So what about the 8th partial sum? We'll show a couple more steps just to kind of help you see why this is true. So if you look at the 8th partial sum, it's the sum of the first 8 terms of the harmonic series, 1 and 1/2, 1/3, 1/4, plus 1/5, 1/6, plus 1/7, plus 1/8. And you compare that to a smaller sum, put 1/4 in for 1/3, 1/4 is smaller. Now put 1/8 in for 1/5 and 1/6 and 1/7, which is smaller. And now you get a sum of 1/2 again, right? 1 and 1/2 plus 2/4 plus 4/8. Now you've got 3/2. So 1 plus 3/2. And so the 2 to the third partial sum is greater than 1 plus 3/2. Yeah, so the 2 to the n partial sum is greater than 1 plus n/2 when n equals 3. And what about the 16th partial sum? Add up all the unit fractions up to 1/16. We can kind of play that same game again. We'll have a smaller sum that's easier to add up. Put in 1/4 there and 1/8 for these fractions, and put in 1/16 for 1/9, 1/10 up through 1/15. And these are smaller, 1/16 smaller, so you end up with a smaller sum. But all these are just 1 plus 1/2 plus 2/4 plus 4/8, which is 1/2, and 8/16, which is 1/2. So you really get 1 plus 4/2, right? Because here you have 4 numbers equal to a half, right? And so that shows the 2 to the 4th partial sum is greater than 1 plus 4/2. And so the 2 to the n partial sum of the harmonic series is greater than 1 plus n/2 when n is 4. And you can show this more rigorously through induction that this is always true for any integer n greater or equal to 2. 2 to the n partial sum is greater than 1 plus n over 2. So this 1 plus n over 2 goes off to infinity. So if you have 2 sequences or series that consist of positive terms, and one, you can correspond them in a way that one of the series has smaller terms of smaller value compared to the corresponding value, and that smaller one goes off to infinity, then the one that's bigger has to go off to infinity too. So since 1 plus n over 2, that's like an increasing line. Think about this as being 1 plus 1/2 n. That's a positive slope. It increases, if you have that as a line. But here it's like a bunch of dots in a line, because we're looking at counting numbers instead of a real number for x. Since this diverges to infinity as n increases without bound, and n increases without bound, it follows that the harmonic series diverges to infinity by the comparison test. So the harmonic series diverges to infinity. It doesn't converge to a number. All right, so we're going to get to talking about the Torricelli's trumpet and use some of this too. All right, so here's the reciprocal function, y equals 1 over x. And so let's think about what numbers you would get. If you started taking reciprocals of positive integers, counting numbers, you get 1/2, 1/3, 1/4, 1/5, 1/6. What about 0? It's undefined, right? Can't divide by 0. 1 over -1, you get -1, minus 1/2. So that's why the graph looks like this. But we're just going to concentrate on the positive part here. We're going to look at the part where consider y equals 1 over x for x greater or equal to 1. So here, x represents a real number, a continuous variable for x on the interval from 1 to infinity. So we're going to look at this. So what we'll do is we'll get Torricelli's trumpet by kind of taking this curve and rotating it about the x-axis, and that'll give us like a three-dimensional volume. So, and it'll look like this. So we'll use a method of approximation of the surface area of Torricelli's trumpet that involves fitting cylinders under the curve y equals 1 over x. So we'll denote by T sub n the surface area of Torricelli's trumpet, but only up to a number n. It's like a finite sum there. Oops, this is real sensitive. Sorry about that. So n's a positive integer. All right, so what we'll do is we'll rotate these rectangles. So we'll put little rectangles underneath that curve, and the top part is, you see in red there. We'll rotate these rectangles in the figure around the x-axis to produce a tower of concentric cylinders, and it kind of resembles a wedding cake, but it's lying down on the side. So, and so this tower is called Torricelli's tower. So if we find the surface area of Torricelli's tower, that'll be small. The lateral surface area of Torricelli's tower, that'll be less than the surface area of Torricelli's trumpet. This tower is called Torricelli's tower. The red line segments in the picture will produce the sides of the different small cylinders. So here's a picture. So we get these cylinders. We're just going to measure the lateral surface area. And we'll compare that to Torricelli's trumpet, which will be bigger because it's above that. To find the lateral surface areas of the cylinders of Torricelli's tower, remember pi is the circumference of a circle divided by the diameter of a circle. And so so that's c, and then the diameter of a circle is 2 times the radius. So pi, the real number pi is c divided by 2r. So if you solve for c, how would you solve that equation for c? If you had pi equals c divided by 2r, how would you get c by itself? Pi equals c divided by 2r. How do you cancel out divide by 2r, right? Yeah, you multiply by 2r, right? So you get that c is 2 pi r. That's a standard formula for the circumference of a circle. Okay, so we'll use that. And so the lateral surface area of one of these cylinders will be 2 pi r times height. Because a cylinder, if you think of just like a can of soda or something, you have like the lateral surface area, that's the circumference of a circle times the height, that's all. And so r is the radius of a cylinder and h is the height of the cylinder. So here we'll use these unit fractions for the radii. That's how, the radius of each of these circles here, concentric circles, and we'll use h, the height will end up being 1 each time. So that'll give us the lateral surface area of Torricelli's tower. Okay, so for any counting number n, the surface area of Torricelli's trumpet is greater than T sub n, because that's the same thing, but it stops just for a counting number n. So it's the whole surface area of Torricelli's trumpet is greater than that. But for each of these two T sub n's, see T sub n is like the sum of the surface area after you've rotated that curve around up to n. But now if you take the lateral surface areas of Torricelli's tower, that's a smaller sum. We have 2 pi r times h, where h is 1, because you have to kind of think the height as being, it's like the cylinders are lying on its side, you know. So each of these heights of these cylinders are like the length of these red line segments. That's equal to 1 each time, so we end up with this. So if we simplify that, yeah, this approximates the lateral surface area of Torricelli's tower, because they're only going up to n. And now, you know, multiply by 1 will simplify. The 1's kind of go away because you multiply by 1 and you get the same number back. And now we'll factor out 2 pi, and we have the sum of it's like the nth partial sum of the harmonic series minus 1, because we took out the 1, right? And so this is 2 pi times the nth partial sum of the harmonic series minus 1. So the surface area of Torricelli's trumpet is larger than this, but now if we take the limit, so for any integer n, we can say this is true, no matter, so n could be as big as you want, it'll still be true. The surface area of Torricelli's trumpet is greater than T sub n, which is the same thing, surface area of Torricelli's trumpet up to a counting number n, and then this is the lateral surface area of Torricelli's tower, which is less. Now if since that's true for any n, we can just let that n get bigger and bigger, and we take the limit, and we'll get the limit of the T sub n gives you the whole surface area of the Torricelli's trumpet, but this will stay below that, but you'll get this limit of this is the whole harmonic series, which is infinite, it diverges to infinity, but if you subtract 1 from infinity and multiply it by a number, it stays infinite. So this diverges since the harmonic series diverges. So that tells you that the surface area of Torricelli's trumpet diverges. It just goes off to infinity. Okay, so you almost can see that in the picture though. You know, if you have like a trumpet, it goes off to infinity, you think, I bet that surface area of that trumpet is infinite. And you're right, but here's the paradoxical thing. We can show that the volume of Torricelli's trumpet is finite. So that's what we'll do next. We'll use some calculus. My calculus students didn't come, so this is something they would understand more probably. We'll use some techniques of calculus, but it'll be good if you don't understand this part. It's good to be exposed to things if you haven't had calculus. To find this volume, this time we'll use the area of a circle. Area equals pi r squared, and we'll look at Torricelli's trumpet, and here's how we'll count up the volume by counting as we go along all these areas of these disks. Kind of think about taking a slice of Torricelli's trumpet, and you'll get like a circle, and we'll add up all those circles. So we need an infinite sum of areas of circles, pi r squared, where r equals 1 over x. That's that curve going down here again, and here x starts at 1 and goes to infinity. So for this, we'll use integral calculus. We'll have pi r squared, and the r is 1 over x, so we'll square it. And then the dx is like a paper-thin width of that disk, and we'll add up those disks going from 1 to infinity. And so this is an improper integral we talked about in Calculus 2 class this semester. So the way you deal with improper integrals, where one of the limits is like infinity, is you let it be a finite number, parameter n, and then you take the limit. So we'll work this definite integral out with n there. And the way you do this is, so the fundamental theorem of calculus allows you to calculate this integral. So we can factor out a pi, because pi doesn't involve the x. It's a constant factor. And then 1 over x squared is the same as x to the minus 2. Now this function is one that has an antiderivative. And this may not make sense if you haven't had calculus, but an antiderivative is a function for which the derivative or derived function equals what we start with, which is x to the minus 2. And so the fundamental theorem of calculus will allow you to calculate the area using antiderivative. And that's all you need to know. But there are rules for how you find derivatives and antiderivatives. And a derivative is, if you have a function, you might want to know the slope of the tangent line at any point on the curve of that function. And the derivative is another function that you get from the formula for the function that tells you the slope of the tangent line at any point along the way. And then the antiderivative is a function whose derivative is a certain something. So it's a little bit, something you have to kind of study calculus for. So what you do to find the antiderivative of this is you add 1 to the exponent and then divide by that new exponent. So if you add 1 to -2, you get -1. You divide by -1. Now this function has a derivative equal to x to the -2. So this, and once again, we won't worry about this. This is kind of calculus stuff. So we'll evaluate the antiderivative now. We'll get minus x minus n to the -1 minus, we put 1 in there, -1 to the -1. Now, but you know this stuff. You're taking college algebra. Some of you are taking college algebra with me. Before you do multiply by -1, you take care of the exponent. And n to the -1 is what? What's n to the -1? It's 1 over n, right? 1 over n to the positive, right? And so you have -1 over n. This is 1 over, reciprocal of 1 is 1 over 1. So you just get minus -1, so that's +1. And then we switch the order just because, you know, we can rewrite it as 1 minus 1 over n. Okay, that's what that is. And this is what we'll take the limit of to get the whole volume of Torricelli's trumpet. So here, you're just restating some things here. So we can find the volume of Torricelli's trumpet by finding the improper integral by taking this limit. But we know this part. That's going to be, put that in there. We'll take the limit of this. Now what happens is n gets bigger and bigger in this expression. The only place where n shows up is right here at 1 over n. So 1 over n as n gets bigger and bigger just goes to 0. And you end up with pi. So guess what the volume of Torricelli's trumpet is that you saw in those pictures? It's pi. It's 3.14. Seems kind of like a small number, right? 3.14, etc. So the volume's pi. So Torricelli's trumpet, even though it has an infinite surface area, it goes off to infinity, it has a finite volume at the same time. So this was kind of a, you know, one of those paradoxical math things that Torricelli was the first to discover. And this also comes up. I was doing a little bit of research. They called it Gabriel's horn, and you know, Gabriel's horn is like on the end of times. You know, Gabriel will blow his horn or something. And I thought, well, maybe it has to do with the fact that in order to blow Torricelli's trumpet or Gabriel's horn, someone would have to overcome infinity to get to the end of it to blow it, because the end where you blow is like infinitely away. I don't know. Maybe that's why they thought of Gabriel's horn, because we never quite get to the judgment day. But sometimes they call that Gabriel's horn also, Torricelli's trumpet. All right, well, any questions? So Jacob Bernoulli's theorem is in this book, and I actually went over that with my Calculus 2 class and my senior analysis class this semester. But I have a few books by William Dunham. He has a great one on just Euler, the great Euler's accomplishments. And Julian Havel's got some good books. So this is where all those pictures of Torricelli's trumpet I got from that book. And then the ones at the beginning about the waves and the notes and all that, and the overtone series came from Harvard Concise Dictionary of Music. All right, well, that's it. Just kind of show where music and math come together in places, and show you kind of a paradoxical math construct that's called Torricelli's trumpet that has a infinite surface area, but at the same time, a finite volume. Let's see. Anything else we need to say here? Any questions or thoughts? So if you're in my class, hopefully you got one of those you can fill out. If there's some, one of the questions is if you have a question that you didn't get a chance to ask, but you would, what is that question? So does anybody have a question about any of this? Well, thanks for coming, and yeah, there's a lot of interesting ways where we have a harmonic series of music or overtone series of music. Sometimes that's called a harmonic series, but then that also shows up in music too, and it really goes back to the quadrivium and seeing rational fractions in music, whole number fractions in music. All right. So yes.
Yeah, I have a small question because you know, my background is about computer science. So we always can write some like a program, right? So we just think about the, you know, the music and the related device, right? Based on the math, this kind of calculation. So we can think about the different music, some like voice something, and the related device connection. Right? So if we program them and use like a 3D print or something, so maybe we can define some, you know, different device which can combine several, like a piano or guitar, several this kind of music system together. Do you think that's possible?
But to combine different instruments using computer science?
Yeah, I mean, for example, now we play music. We have some guitar, right? So some people playing guitar, some playing piano, right?
Yeah.
So okay, so now I design one device with the two functions, piano function and the guitar function.
But
I don't know what
function you said?
I mean, I just use one device. I can play the music with the function from piano and the function from guitar.
Guitar.
Guitar, right?
Guitar.
Because before one guy playing guitar, another guy playing piano, right? So now I don't know. So we can get at least two music, and each music how about related math function, and then related this kind of possible like a 3D device, some shape.
It reminds me of something that's been around since the 80s, which is like a MIDI, where you could make a music that you had recorded. You could almost change the sound of the music into something else. And you could change the sound of a guitar using like a MIDI system. And I don't quite understand all of that, but there, it also reminds me when you have keyboards, a lot of times you have different voices, and one might be like, this keyboard sounds supposed to sound like a trumpet. This is supposed to sound like strings or organ or marimba or something. And so that kind of reminds me of what you were saying, but I'm not sure if that's quite what you had in mind, though. We have different instruments or voices from a keyboard. All right, thanks for coming, and if we have more questions, be sure and hand in your, for one of my current students, get your questionnaire handed in. And if you didn't make it today and you've already watched this and you wonder, if you've watched this on a recording later, then I'll probably also put this up so you can fill it out to get extra credit.